Hello, everybody. We're going to get started now. Sorry for the little bit of the delay. I was uploading our stream to our YouTube live channel as well. Today's topic is going to be about ocean chemistry. Please refrain from using the chat section of the Zoom here until the end when we will have a Q&A period. If you are on YouTube live, I will try and answer the questions after the live stream. All of our resources will be on our website about an hour after this broadcast. If this is your first time joining us for a webinar, thanks so much. I just want to quickly tell those who haven't joined us who OPAC is. OPAC stands for Ocean Protection Advocacy Kids, and OPAC is based out of Plymouth, Massachusetts. We do travel around though, and we teach marine science, art, and advocacy workshops for students in grades K through 12. Unique to our programs is that we focus heavily on the art and advocacy piece so that our students can become the next generation of ocean advocates and really give the ocean the voice that it needs because it can't speak up for itself. All right, so today's topic is, going to be ocean chemistry, which as oceanographers we call chemical oceanography. We're going to define what that means. We're going to investigate some properties of water that allow all of these things to happen. We're going to take a little bit of a dive into some of the important nutrients in our ocean. We're going to study a little bit about how volcanoes impact ocean chemistry. And we're going to highlight the need for some water quality testing. I am going to show you some kits that you can purchase at home to do your own water quality testing and join a citizen science effort. And we're going to learn how to do an ocean acidification experiment at your own home. And then at the end, we will have that Q&A time for you to ask any questions. So I do want to start this lesson off with a few definitions, just so we're all on the same page about what some things mean. First being chemistry, since this is about ocean chemistry. So when we're talking about chemistry, we're just talking about the science around elements and compounds and how these things change, what their composition is. And we're going to be talking a lot about how energy transfers through these systems versus geology, which is talking about the solid elements on our planet, which when we're talking about chemistry, geology is very closely related, especially in the ocean. And then we have biology, which is the study of our living things and their processes. And again, if we're talking about chemistry, we're usually talking about biological processes as well. They're very closely related. We're going to talk a little bit about pH, and pH is important in chemistry. When we're talking about pH, we're talking about how acidic or basic something is. And we do this on a scale from 0 to 14, which is really just measuring the concentration of our hydrogen ions in a substance or a liquid. An element, this is something that can't be broken down into other substances. So think of oxygen, carbon, phosphorus, nitrogen, the things on the periodic table. And then we have nutrients, which when I'm talking about a nutrient today, we're talking kind of about the next level of an element. So if I'm talking about the nutrient nitrogen, I'm not always talking about just nitrogen. It could be the forms of nitrogen that we find in the ocean, like nitrate or nitrite. So that's just a little bit of a difference there, but nutrients, you can think of elements for the basis of the conversation we're going to have. All right, so what is this ocean chemistry that we are studying? We're going to use this definition of chemical oceanography, which is the study of pathways that chemical species follow through their transit of the ocean. When we're talking about this transit, We're talking about things on a really tiny scale, the molecular scale, all the way up to our global cycles. And ocean chemistry takes place on numerous time scales. So we have things that are happening all around us every second of every minute of every day. And then we have processes more on the geological side that are taking billions of years to form. So think of the process of fossil fuels forming, like the creation of coal. And as I mentioned in our definitions, chemical oceanography is very closely related to biological and geological processes. To put that into perspective, this is just a quick figure to show you how chemical processes are happening over large timescales and large areas of our planet. So think of things like sediment exchange, or how things move between the bottom of our ocean floor, or if you're on the land, how things are decomposing over large periods of time on the crust. You don't really need to go too much further into this, but I think it's a good visual of that time scale. So I do want to talk a little bit about why water is so important and how that those properties of water influence our ocean chemistry. So water has some super cool properties. First of all, we have cohesion, which allows those water molecules to stick together. And they do that to kind of be together, which is where we get that surface tension of the water as well. And all of that's possible from the polarity of water. And when we're talking about polarity, if you look at the little figure here, you can see little tiny plus and minus signs. It's kind of like a battery, and water has a slightly positive and slightly negative charge. So we call that dipolar, and the dipolarity, the polarity creates little tiny batteries in essence. Water is also super important because it's a universal solvent, which means that most things will dissolve in water if left in water over a long period of time. So think of things like salt. Water is super powerful at breaking apart other molecules' bonds. So it has extreme capacity to pull apart those charges on other things like your typical table salt, sodium chloride. Heat capacities are a really cool property of water. So water, it's actually really hard to change the temperature of water, which is what we're thinking about when we're thinking about heat capacity. So it takes a lot of heat energy to change the temperature, so the degrees of our water, which when we're talking about our oceans, which cover 71% of our globe, it takes a lot of energy to change the overall temperature of the ocean, which then goes into latent heat, which is a fancy term for how much energy it takes to go from different phases of water. So we have, liquid, solid, gas, which is going to be important later on when we're talking about how nutrients get into the water. But just remember, it takes a lot of energy to get the ocean to freeze or to evaporate. And then density, I'm putting in there as a plug for Thursday's webinar. Our ocean has a lot of temperature and salinity changes and pressure from the amount of water depth. So little tiny changes in density can create currents in the water, and our webinar on Thursday is about ocean circulation. So we're going to talk a lot about density on Thursday. There is a fun little video about the properties of water that I will link to our website after this. This is just showing you a little bit about how that density changes over latitudes. So if you think about the warmer parts of our globe, so near the equator, we have a lot of evaporation happening, which then moves, changes the salinity of that water, and then we'll move the evaporated water up to our precipitation latitudes, our colder areas of the globe. And we're going to talk a little bit more about that on Thursday. So this is a cool little video that talks about how much salt there actually is in our ocean. I'm just going to play that quickly for you. Awesome. So we're going to talk a little bit more about the importance of calcium for marine creatures at the end of this webinar. But it's important to measure a lot of the things that were mentioned in the video so that we can both have a baseline for what our ocean should look like, and so that we can monitor changes and how those changes impact geological and biological cycles as well. So there are some common things that we do measure in our oceans. Temperature. So why is it important to measure temperature? Think about ourselves as humans. We like to have an ideal climate. There are many organisms in the ocean that with small temperature changes can no longer survive. Salinity, which we've mentioned, salinity drives density and density drives currents. And if our currents slow down, our climate can change. So salinity is really important to pay attention to. pH. So if you are something that relies on a calcium carbonate shell, if the pH in the water is changing dramatically, your shell might start to dissolve, which is not a good thing. But other things that pH drives are how many different nutrients are being dissolved in something. Dissolved oxygen, believe it or not, everything needs to breathe. And when we have lower rates of dissolved oxygen in the water, we get dead zones in the ocean where things no longer survive. Turbidity is one that most people haven't heard of out of this list of things that we measure. Turbidity is looking at how much stuff is in the water. So it's looking at all the little particles and things that we might not measure when we're talking about salinity, which is just looking at the total amount of solid materials that are dissolved in water, versus turbidity, which is looking at all the particles that are dissolved in water, including the organic things. We measure chlorophyll to see how much phytoplankton is in the water, and phytoplankton is the base of our marine food web. If you want to learn more about phytoplankton, we did a webinar last week on plankton, which you can find on our website. We do like to measure the concentrations of nutrients in the water, because the changes in nutrients can tell us what different organisms are living in the water. It can tell us what's limiting growth for those organisms. And it can also tell us a little bit about the sediment and maybe where things have come from on other parts of the planet. And now we are measuring things like plastic and other pollutants in the water because we've put them there. So the average salinity of the ocean, which is our benchmark to see if something's more salty or less salty, is about 35 parts per thousand, or 3.5% by weight. Within that, though, the major things that make up that 3.5% are dissolved chloride, sodium, sulfate, magnesium, calcium, and potassium. So those are the major dissolved substances that we would find that make the ocean salty. The average temperature of the ocean depends on if you're at the surface, which is usually around 17 degrees Celsius. Again, that's an average of the entire globe, including our polar and equator regions. But at the deep ocean, our water is actually very, very cold, between 0 and 3 degrees Celsius, so almost frozen. The average pH of the ocean at the surface is closer to 8.1, between 8.1 and 8.2. And that number actually gets more acidic, so closer to 0. So around 7.5 or so, 7.6, when you get deeper in the ocean, and that's because there is more carbon dioxide, and colder water absorbs more nutrients than warmer water. The average depth of our ocean is 2.3 miles, and so I put that in there just to show you that when we're talking about these averages, we're talking about a lot of water. We find the highest nutrient concentrations closer to land because there's more runoff at the ends of rivers, near hydrothermal vents, which are underwater volcanoes, and in colder water. It's important to remember that colder water absorbs more nutrients than warmer water. And what happens if there isn't enough oxygen in the water? We get those dead zones that I mentioned previously. And a dead zone, it occurs because we get a really high flux of nutrients, which creates an algal bloom. So those phytoplankton grow really, really fast. But then when the phytoplankton die, they decompose and they take the oxygen back out of the water. And then our oxygen level drops to a point that is dangerous for our fish and our megafauna that require the oxygen to survive. So talking about all these elements, how do they actually get into the ocean? Why isn't the ocean fresh water? And it starts off with things that are coming out of our rivers, which were mentioned in the video there, and our groundwater. So if you're on the coast and you have septic systems and things, all of the nutrients from that can leach into our water or spread into the water. We have hydrothermal processes, which if you're looking at the figure here, where it says mantle and hydrothermal vents in the middle of that figure, we have volcanic eruptions happening all the time at the bottom of the ocean, which are releasing nutrients that get mixed into the water. We have seawater and sediment interaction. So think about being at the beach and a wave hitting the beach, and you can see all of the sand getting churned up. We're always having sediment getting released back into the water column. We have the gas exchange between the air and the sea. So think about the constant evaporation and precipitation that are happening. And then we also have other atmospheric things like volcanic ash and dust being blown from deserts and land into the ocean, which all create this chemistry of our ocean. So why test for these nutrients? Why are they so important? The main reason is that it's theorized that biology controls the chemical makeup of the ocean. So we need to understand what's limiting the growth of the organisms that live there. And if we monitor these nutrients over time, we can understand maybe what we would need to add to a certain system to help a certain species grow or thrive, or to limit the growth of a species that is there. For example, more carbon in the ocean, would it have a positive or negative impact on an ecosystem? Think about ocean acidification. If we add more carbon to the system, we might be taking carbon out of the atmosphere, but we're hurting creatures that have calcium carbonate shells because we're making it more acidic in the ocean. But then there are nutrients in the ocean that are harder to test because there isn't a lot of it in the ocean, things like iron. And I do have a short little video for you on how we would actually go out and test these limiting nutrients in the oceans, things that we don't have a lot of, because organisms still need them, and if they don't have them, we don't find them in certain areas. And there have actually been experiments with trying to fertilize the ocean with iron. So I just want to show you how we'd actually go out and collect something that is of what we call a trace element, very hard to find.
The amount of iron in the ocean, it's vanishingly small. If you think about an Olympic-sized swimming pool, the amount of iron in the open ocean is literally represented by just a drop of water in that swimming pool. I'm Kathy Barbeau, and I'm a marine chemist and a professor at the Scripps Institution of Oceanography. I study the biogeochemical cycling of trace elements in the marine environment, so primarily iron, which can be an important micronutrient for phytoplankton in the open ocean. Those few atoms of iron play a crucial role in important enzymatic reactions, photosynthesis, respiration, and in the larger overall global cycling of carbon and nitrogen. I work in both the field and in the laboratory in my research. In the field, as a trace metal chemist, the big challenge for me is to try and get clean samples, to go out on this large metal object and sample the surrounding seawater where metals are present at vanishingly low concentrations and not contaminate your sample. So I have a rosette with special bottles and special cables that I use. When I go to sea, I also bring a clean laboratory with me that we set up with a positive pressure, everything non-metallic materials, and that's where we process our samples. I work on the interface between chemistry and biology, so I also use genomic tools to look at how trace elements like iron cycle in seawater so that we can understand what's happening now, what's happened in the past, and what's going to happen going forward.
So again, we have things like iron that are very limited in the ocean, but very important for plankton and other creatures out there. So when we start looking at all of these nutrients and we average them all together, something pretty cool happens. And a scientist named Redfield in the 1930s started to put together this hypothesis that when you measure the nitrogen and phosphorus levels, they have a ratio of 16 nitrogen to 1 phosphorus throughout the entire ocean. And that will vary depending on where you are. But again, that's the average of all of that in the ocean. And that can start to show us what limiting nutrients are out there. And when I say limiting nutrients, I'm saying if you're a plankton that needs more nitrogen, then you might survive in certain habitats better than other habitats versus if you're more reliant on phosphorus, and understanding that there's an average can show us where we have higher levels of nitrogen and how that gets moved around in different parts of the ocean. This is useful for modeling and predicting what those limited nutrients are, like I just said. This ratio also shows us that biology controls the chemical makeup of the ocean. Again, looking at what individual organisms need to survive on a chemical level. And this can be extended out to look at other elements like iron and nitrogen. Sorry, thought I had a different slide there. So this ratio can be extended out to include elements like silica and iron and magnesium to show us what individual organisms need to thrive. So once we get past understanding where our nutrients have come from when they enter the ocean and how they might be limiting, we can then look at individual cycles of elements. And I don't want to go into the itty-bitty parts of this figure. I just want to show you that it's very complicated when we're talking about different nutrients. And there's, once you have one form of an element like nitrogen, it can change into many different forms and enter into the system, exit the system, be used and recycled. It's very complicated, but I just wanted to point out that each element does have its own chemical cycle and they are reliant on each other. One big thing that we talked about is carbon and how we can store carbon in the ocean. And one way is through what we call the solubility pump, which is the figure on the left. And as I mentioned earlier, colder water has a better ability at absorbing nutrients. So in our higher latitudes, think our polar regions, the Antarctic and Arctic areas of our globe, the poles, we have the ability to draw in more CO2 into that colder water. And then our currents, which we're going to learn about on Thursday, will take that water and bring it down to the deep ocean and transport it around the globe where it can stay there for a very long time. The downside to our solubility pump is that when that water then reaches our lower latitudes near our equator, it can then be upwelled or brought back to the surface, and that carbon can be released. But oftentimes, as that CO2 gets absorbed into the water column, it will enter another pump that we call the biological pump, where that carbon will be used from phytoplankton or then eaten by zooplankton, and all those things will die and then settle down to the ocean floor, where that carbon can then be stored for a very long period of time. So the difference there is our solubility pump is just taking carbon out of the atmosphere, absorbing it into the ocean. It's staying in the system, versus our biological pump, where the carbon is being taken up by biological organisms like plankton. And then when those things die, they have a higher chance of reaching the sea floor, because the carbon is in an organic substance like plankton, where it has more weight and isn't just in the water, it's another substance. I briefly mentioned earlier that we have iron fertilization. So if there was a part of the ocean that maybe we wanted to create more plankton from, we could add iron to it. So think of like your garden and adding nutrients, and there have been a lot of experiments that have tried to actually increase the rate of primary production, so that how much plankton is being made in part of the ocean. And it takes a lot of iron to do this, because if we think about that Redfield ratio that I just told you, we would need a lot of iron for the amount of phosphorus and nitrogen that would be in the ocean. So it didn't really go very far, but the idea was to bring boats out and dump a whole bunch of iron and create more phytoplankton blooms to bring carbon into the ocean and hopefully sequester it over time. So the whole idea behind the fertilization was to draw carbon out of the atmosphere. I'll share a couple of links on this process. There's a lot of debate on whether it's a good idea or a bad idea in the scientific community. So it's pretty cool to talk about volcanoes. I wish we might actually do a webinar next week on underwater volcanoes or hydrothermal vents. But for today, I want to talk more about volcanoes on land and their impact on our oceans. So if we have a big eruption, we're putting a lot of things into the atmosphere, and we're usually thinking about like metals and iron that can then disperse out into the ocean. And in 2018, we had an eruption in Hawaii, which I'm probably going to butcher the pronunciation on this. My apologies, but I think it's Kilauea. Was the name of the volcano that erupted. And in Hawaii, the ocean usually has something called picoplankton, which are really tiny plankton and they're really tiny because there aren't a lot of nutrients in the water, because it's near the equator, which is warmer water, which again holds less nutrients. And when this volcano erupted, all of a sudden there were really big plankton like diatoms, and scientists were really confused, and they thought initially it was because the volcano was dumping the iron into the ocean, but quickly found out that the iron that was being deposited wasn't actually usable by the plankton, because it hadn't converted into the form that plankton would need yet. And what we found out is that the volcano actually changed the current of the water. So it was mixing the water. So it was bringing colder water up to the surface, which we call upwelling, which brought all those nutrients, and the levels of nitrogen spiked really high. And we got those bigger plankton, the diatoms. So it wasn't actually the iron from the volcanoes, it was that the volcano changed the physics of the ocean. So even one step further, we're now not just talking about biology, geology. A volcano can change the physics, and then everything else changes down the line. That being said, volcanoes do bring a lot of those micronutrients like iron into the ocean, but it does take time for them to convert into usable forms for our organisms. And then on the right here, we do just have a quick diagram of those hydrothermal vents, which, like I said, I think we're going to do a webinar on next week. And those are spewing out all across the ridges of our ocean, the underwater mountains, and those are releasing metals into the ocean and sulfur, a lot of sulfur, which then are transported around the planet through those currents, which we're going to talk about on Thursday. So when we're talking about ocean chemistry, we often talk about water quality and what qualifies as good water or clean water. And it really depends on what you're trying to justify. Is the water safe for drinking? Is the water safe for swimming? Is the water safe for watering your garden? Is the water safe for fish to swim in? Is there enough oxygen in the water for fish to swim in? So water quality is really just a measure of the suitability of that water depending on what you're trying to measure. And that goes back to measuring the temperature, the salinity, the pH, dissolved oxygen. And we now have parameters for what justifies good, and it depends on, again, on what you're trying to, what your end result is. Is it good for swimming? Is it good for drinking, etc.? And OPAC is partners with an organization called Earth Echo International, which is founded by Philippe Cousteau. And they have a wonderful citizen science effort for measuring water quality all across the globe, and millions of participants take part in this every year. And you can go on their website, and I will put the link, and you can get your own water quality kit to do water quality testing in the freshwater or saltwater near your house when it's safe to do that. And the kit will help you measure turbidity, temperature, as well as pH and dissolved oxygen. So you can really get a sense of how good your water is, depending on what you're trying to figure out for that question. I want to quickly look at ocean acidification a little bit deeper, because the experiment that I have for you to do at home is all about ocean acidification.
Invisible force invades world, slowly dissolving residents. Sounds like science fiction. Actually, it's science nonfiction, otherwise known as reality, and it's happening right now. It is ocean acidification. The ocean absorbs about 1/3 of the carbon dioxide that spews forth from our cars, factories, power plants, and airplanes. That's over 22 million tons of CO2 a day. But the ocean doesn't just absorb all that CO2. There's a chemical reaction going on here. Through processes involving hydrogen ions and other sciencey nonfiction words, the ocean is becoming more acidic. And that in turn is eroding the shells of vital marine species, including clams, oysters, urchins, and pteropods. Oh sure, I know what you're thinking. Who cares about a bunch of pteropods? But these animals are part of the foundation of an enormous food web. And when little things change on a big scale, big changes are sure to follow. The chemical change in our seawater is also having an effect on corals. In fact, scientists say that ocean acidification could wipe out most coral reefs by the middle of this century. It's affecting larger animals too. For example, certain fish have a harder time detecting predators, and that's just for starters. The good news is that with less carbon pollution, the ocean should regain its chemical balance. If not, the truth will be a lot scarier than fiction.
All right, so ocean acidification is one easy way to see how climate change is impacting our oceans. It's also a good explanation of ocean chemistry and seeing how little things can make a big difference in our biological world as well. And I'm gonna host an experiment that you can do at home, and all you're going to need are either some shells or pieces of chalk and some vinegar and water, and you can actually measure the changes in that seashell or chalk over time. And vinegar is definitely a lot stronger than what the acidity of our ocean is, but it will show you how when you increase the acidity of the water that these creatures are living in, it really does change their the thickness of their shell, the appearance of their shell. And again, I'll have all the details for that on our website in about an hour. And I will link that video for you to watch again, as well as another explanation of ocean acidification. I will have some other follow-up things for you as well on our website, including the information on how to get your own citizen science kit from Earth Echo International. Please stay tuned to the ocean art contest that I've been promoting for the last week. Some of those deadlines are coming up. And then I'm going to have some news articles and more videos for you about ocean chemistry and ocean acidification on our website. And please join us again on Thursday for ocean circulation, which we're going to talk again, which some of the things that we talked about today will definitely be prevalent for on Thursday. I'm just going to now take a little bit of time to answer people's questions about ocean chemistry. All right, so if you have questions, you can pop them in now. If you have any questions, you can throw them in the chat or the Q&A on Zoom. And if you're on YouTube, I will try and answer them after the broadcast. If I don't see any questions here in the next minute or so, I will just sign out. I see a question here. If salinity is rising due to greater evaporation from heat, how come there's also oceans rising? Great question. So we do have higher rates of evaporation, but think about where that water is going into our atmosphere, where that can be deposited into other parts of our planet. And higher rates, higher temperatures also mean that we're increasing the temperature of the ocean, which is going to impact our icebergs. And when we melt ice, we're creating higher seas. I hope that helps that question. So higher evaporation pretty much means overall we have a warmer ocean, which can melt a lot of the ice that we rely on for keeping our seas from rising. Another question, is a lot of plankton bad or good? That depends. Too much of anything isn't good. So think about those dead zones that I mentioned. If we have too much plankton, that plankton does eventually die. When that plankton dies, it's going to decompose, and it's going to do the opposite of photosynthesis and take the oxygen back out of the water, and then we don't have enough oxygen for our fish to breathe. Did the experiment with the iron work? So there were many examples of adding iron to systems where we did get more plankton, but it takes a lot of iron to get a little bit of plankton, and it wasn't doing enough for it to be really feasible all over the place. And when we start changing the natural ecosystems that are out there, we don't always understand all of the repercussions down the line from that. what impact does this have on coral, both hard and soft? One of the links that I will have on our website does talk a little bit more about the difference between hard and soft. But overall, if we're adding more carbon to the atmosphere and it's being sequestered by the ocean, if we're increasing the acidity and you have calcium carbonate shell, it's going to negatively impact you either way. How much iron would it take to get enough plankton in the ocean? It's not that we don't have enough plankton, there's just parts of the ocean that have like a lot of sunlight, but not a lot of nutrients. And if we add more of that iron, we can get bigger plankton that would then take more CO2 out of the atmosphere. It's just a lot of wacky ways to change the normal ecosystem that's there. All right, I'm not seeing any more questions right now, but please feel free to shoot us an email or send us a question on Facebook. We're more than happy to answer them all week. And just a reminder that we do have another, where is it here? That we do have another webinar coming up on Thursday. It's all about ocean circulation. And then we will have more things for you coming up in the next couple weeks. So as long as school is closed, we will be here talking about the ocean. If there's anything that you really want to learn about, send us an email and maybe we can put together a webinar for you. And again, thank you to everyone that has helped us put these out here for free with supporting us on our website. And we look forward to seeing you on Thursday. Bye.